rational numbers and equations. We're going to start off with section 1 on rational numbers. Now, if you don't know what a rational number is, I'm going to go ahead and define it right here. A rational number is a number that can be written as a quotient. Quotient, remember, means division of two integers, and this includes integers themselves. A lot of times we think of it as like a over b, where a and b are both integers, and b is not equal to 0, because you can't have a division of 0. So even though it's considered division, we're used to them as fractions. Rational numbers and fractions kind of mean the same thing to the everyday student. Now, in this first example, it says, show that the number is rational by writing it as a quotient of two integers. What they mean is, write it like a fraction. Well, anytime you have an integer, like 5, and you want to write it as a fraction, the easiest way is just to put it over 1. 5 divided by 1 is 5, and it's written as a fraction, as a rational number, as a quotient of two integers. Same thing here with -3, just put it over 1. Not over -1, because a negative divided by a negative is positive. Put it over +1, -3 over 1. Now, you may remember that when you have a mixed number like this, and if you wanted to change it to a fraction, to an improper fraction, you take the denominator, you multiply it times the whole number out in front, that'd be 6, and then you add that on to the numerator. 6 plus 1 is 7, and we leave this as 7 over 3. You keep the same denominator. 2 1/3 is the same thing as 7 over 3. In 7 over 3 form, you can see it's written as a quotient of two integers. Here's another integer, just put it over 1. The nice thing about 0 is if you put it over 1, put it over 2, put it over a million, it's still 0. 0 over any non-zero number is equal to 0. Now, -3 1/2, I'm going to work it like I did the 2 1/3. It's just that it's going to have the negative sign with it. 2 times 3 is 6, plus 1 is 7, so I'm going to write this as -7 over 2. -7 over 2. Now, the last one I have is a decimal. A decimal is just a fancy-looking fraction, because what happens is the place value, which is in the 10th spot for the 3, indicates the denominator. The denominator is 10. This is the same as 3 over 10, 3/10. And I've written it as a fraction. All right, now remember, a over b means a divided by b. You're taking the numerator, dividing it by the denominator. We leave it in this form so that we have something convenient to work with, because if we actually do the division, we're going to get a decimal. Now, when you're getting decimals from rational numbers, you're going to get one of two kinds of decimals. You're either going to get a terminating decimal, and you know what terminate means, right? That means to end. Terminate means that the decimal end will end somewhere, and when you're doing the division, you'll eventually get nothing but zeros. There won't be anything to bring down but zeros, and you won't bring anything up but zeros. A repeating decimal is the other possibility. What that means is one digit, or maybe 2 digits, or a whole block of digits might be repeating. So you might have something like 0.725, 725, 725, 725, and it repeats, notice, without end. So it's non-terminating, but it's repeating. So when you have a rational number and you write it as a decimal, one of two things occurs. You either get a terminating decimal or you get a repeating decimal. Okay, let's go ahead and let's change some fractions into decimals. Now, it's because they're rational numbers, we're either going to get a terminating decimal or we're going to get a repeating decimal. In the first one, I have 3 over 4, or 3/4. You divide the 4, the denominator, into the numerator. You're going to have to add a decimal point and some zeros. If you don't add enough zeros, you can always put some more. If you add too many, you can erase them. The decimal point will come straight up in the answer. 4 doesn't divide into 3, but 4 divides into 30 7 times. 7 times 4 is 28. I subtract. I bring down a 0. 4 goes into 25 times. 20 on the nose. Nothing left over to bring down but zeros. Nothing left over here. So this is equal to 0.75. This is what we call a terminating decimal. It stops after the second decimal place. Now, in the next example, I know it's negative. I'm going to divide 6 into 5, and I'll add some zeros. I'll bring the decimal point straight up. 6 doesn't divide into 5. 0 times. 6 goes into 58 times. 8 times 6 is 48. I subtract 2, bring down the 0. 6 goes into 20. 3 times. 3 times 6 is 18. Subtract 2, bring down a 0, and you can start to see the pattern develop. It's going to go in 3 times again. 3 times 6 is 18. 18 subtract 2, bring down to 0. It's just going to continue this pattern. You have a repeating pattern here with the digit 3. So you can write this a couple different ways. You can write this as 0.833 and then add like 3 dots on the end. It means and so on. Or better is negative 0.83 and then you put a little bar above the 3 to indicate that that is the only digit that is repeating. That the 3's would continue forever and ever and ever. Now this again is an example. And you can write it, like I said, either way. This is an example of a repeating decimal. It's a rational number, but in decimal form it repeats. Now my last example, before I change this into a decimal, I'm going to go ahead and think of this as 67 over 20. I changed it from a mixed number into an improper fraction. Now I'll do the division. 20 goes into 67, and I'll add some zeros, my decimal point. 20 doesn't go into 6, goes into 67 3 times. There's the 3. That's 60, subtract 7, bring down the 0, goes in 3 times again. 60, subtract 1 0. Now before you jump the gun and think, oh, it's repeating, 3's are going to repeat, you got to keep going and see if you get that same pattern, that same number to come up each time. And if I bring down the 0, 20 goes into 100 5 times evenly. Nothing left over, nothing but zeros to bring down. I can go ahead and just get rid of that. And my answer is 3.35, or 3 35 hundredths. Now that's the proper way to say a decimal, is to use the decimal place. But we get lazy and we'll say 3, or at least I do, and I'll say 3.35 instead of 3 35 hundredths, just for the convenience of it. And that is a terminating decimal. Now in this next example, it says it's a kind of a story problem setup. At the Mallard Park townhouses, there are 52 rental units, of which 13 of them are currently vacant. At the Goose Run Apartments, there are 148 rental units, and 36 of them are vacant. At which property is the vacancy rate greater? Well, the rate at Mallard Park townhouses, would be 13 out of 52. The rate at the Goose Run Apartments would be 36 vacant out of 148. Because they do not have the same denominator, it's very difficult to tell which one is greater. So what I'm going to do is I'm going to change them to decimals and then compare their decimal place values. So I have to do 2 divisions. I have to divide 52 into 13, and I have to divide 148 into 36. So I'll add a decimal point and some zeros. I'll add a decimal point and some zeros. And now I have some long division to do. 52 doesn't divide into 1 or into 13, but it will divide into 130 2 times. 2 times 52 is 104. I'll subtract, that's 26. I'll bring down the 0. 52 goes into that 5 times, as it turns out nicely, with 0 remainder. So I don't need this last 0, so it's 0.25. Over here, 148 doesn't divide into 3, it doesn't divide into 36, but we'll go into 360 2 times. So far they match. 2 times that would be 296. I subtract 4, 6, and I bring down a 0. This goes into that, let's see, 14, I'm guessing about 4 times. I don't think it's got enough for 5. Let me try 4. 4 times that, that'd be a 2, carry a 3, a 9, carry a 1, a 5. I think I got it right. So that's an 8, and that's a 4, and then I would bring down the 0, and I would continue the process. Well, I can stop now, because even if this goes on and eventually starts to repeat or terminates, I can see that this one and this one, by looking at the 100th spot, this value is greater than that. They have the same tenths, but this one has more hundredths. So this is the greater number out of the 2 decimals. You compare them by place value. So that means that it's the Mallard Park townhouses that have the higher vacancy rate at this time. All right, now let's reverse this around. Let's write decimals as fractions. So if we have terminating decimals, the key is to use the place value of the last digit as the denominator. So you can see here, here's my last digit. It's in the 10th spot. So my denominator is going to be a 10. My numerator is going to be what this number would be without the decimal point, which would be 0.8 or just 8. And in this case, this one could reduce. I could divide top and bottom by 2, and I would get 4/5. That would be 0.8 as a fraction in simplest form. Now in this case, my last digit is in the hundredth spot. So my denominator is going to be 100. Now I have a negative, I'll put that out in front, and the number without the decimal point is 217. So it's an improper fraction, but there it is, it's negative 217 over 100. Now if you wanted to change this into a mixed number, you would divide, you would get negative. 100 goes in 2 times with 17 left over, and you have 17 over 100, which does not reduce. On my third example here, I have tenths, hundredths, thousands. So my denominator is going to be 1,000, and my numerator is going to be what this number is without the decimal point, or 9,421, 9,421. If you want to change this into a mixed number, you divide. 1,000 goes into 9,421 9 times with 421 left over, all over 1,000. And fortunately for me, that one does not simplify either, so I don't have to do any additional steps. And there they are as improper and as mixed, these last 2 examples. Now let's look at repeating decimals. Now repeating decimals, we're going to use the nines trick, which I'm going to show you here in just a second, but I'm going to show you the traditional way to do this. If we set this number here, repeating 3s, 3, 3, 3, 3, 3, forever and ever and ever, if I call this x, x equals 0.333, and the 3's go on forever and ever and ever. And then I take this equation and I multiply both sides by 10. This side would be 10x. This side over here would slide the decimal 1 spot, and I would get 3.333, and the 3's go on forever and ever and ever. Now, if I subtract the left sides and the right sides, I subtract this from that, because they're equal amounts, it should make sense. I'm subtracting essentially the same number from both sides, just in equal amounts. And if I do that, 10x minus 1x is 9x. And all these decimal places would subtract and cancel out. And that would leave me 3 minus 0, which is 3. So I have 9x equals 3. I divide by 9 to solve for x. And I get x is equal to 3 over 9, or 1/3 if I reduce. So remember what x was. It was the repeating 3, so this is equal to 1/3. Now that's a lot to do. So I'm going to show you the nines trick. You've got one repeating digit, so you put it over 9. See how the 3 would go over the 9 and then simplify if necessary. This one simplifies. Here I have 2 repeating digits, the 4, 5, 4, 5, 4, 5. So I'm going to use 2 9s. I'm going to write this as 45 over 99. And then if it simplifies, and it does, because I could divide top and bottom here by 9, this reduces to 5 over 11, and that's my answer. This one's got 3 digits that are repeating, so I have to have 3 9s. This is going to be negative because of that. 721 all over 999. Now, if I'm lucky, it's in simplest form, and I believe that one is. I don't think anything will divide top and bottom there. And that's my answer. So it's a lot less work than going through all these steps. So remember the nines trick. It's all based on how many of the digits are repeating. All right, I want to compare with greater than, less than, or equal to these 2 decimals. Now I have here a terminating decimal, 0.3. I have a repeating decimal here, 0.33333, and so on and so on. So if I compare them, all I'm going to do here, actually leave this one the same, I'm going to write this with a couple extra 3's in there. And you can see they have the same number of tenths, but this has 300ths and this one doesn't have a spot here, so it'd be like a 0. So this is the greater number, and I would have to use a less than to indicate the smaller number less than the larger number. Now when I'm comparing 2 fractions that don't have the same denominator, I either can rewrite them to have the same denominator, or I can use cross products. So what I'm going to do is I'm going to take this denominator times this numerator, and I'm going to multiply it, and I'm going to put it right there. 6 times 3 is 18. Now I'm going to take this denominator times this numerator. I'm going to cross multiply. I'm going to put it right there. 20 times 1 is 20. Now I drew the little arrows, or what I call the elephant ears there, so you can make sure that you put the products on the right side. You don't want to multiply 6 times 3 and put it on over here on the right, and the 20 times 1 on the left. You get everything backward. Now I know 18 is less than 20. So I know 3/20 is less than, hopefully you can see that, than 1/6. Now, on this last example, it says order these numbers, and I have a whole bunch of numbers, some of them decimals, some of them fractions, from least to greatest, and I think I'm going to use the number line to help me here. So I'm going to go, let's see, I want to make sure I have enough. I'll go from negative, I don't think I need as far as negative 3, -2, -1, 0, 1, 2, 3, and 4. I don't think I'll need that many. 2.7, that would be right about here. 2.7. And then 0.55, that's a little greater than 0.5, which is a half, so it would be about here, 0.55. Then I have negative 0.9, that's to the left of the 0, not quite at -1, maybe about here, negative 0.9. 9/4. Now 9/4 is tricky because it's an improper fraction, but 4 goes in the 9 2 times with 1 left over. So 2 1/4, that'd be, it's 2 1/2, 2 1/4 would be about here. So I'll put my 9/4 here. Negative 9/8, that's like negative 1 1/8. 8 goes in 9 one time with 1 left over. So that'd be to this side of the -1, about here we'll say. So that would be negative 9/8. And then 13/7. 7 goes in 13 one time with 6 left over. So that's not quite 2. That'd be over here somewhere at 13/7. Now I can see easily on the number line from least to greatest, I would have negative 9/8, negative 0.9, 0.55, 13/7, 9/4, and 2.7. And there's my answer from least to greatest. You can get good at this, but again, like always, practice, practice, practice.